好的，Hello，大家晚上好，欢迎来到原力区直播间，我是原力区 Justin，很高兴呢又和大家见面了。今天是我们 Web3 Infinity Hackathon 的第5期 workshop 直播。Hey guys, good evening. Welcome to the 5th session of the Web3 Infinity Hackathon workshop live stream. I'm Justin from Forest Community, and I'm your host tonight. 那首先呢，我们的 Web3 Infinity Hackathon，它作为新加坡峰会最强的周边赛事，目前已经汇集了上百人报名参与。在这里呢，我们也鼓励和呼吁更多感兴趣的朋友不要犹豫，向我们投递你的作品。目前我们的报名通道已于7月1日正式开放了，将在北京时间8月17日23点45分前截止报名。那参赛团队均可以通过 DevPost 平台提交符合要求的项目。同时呢，作为此次黑客松的最重磅福利之一，我们原力区也将持续在原力直播间为大家邀请到更多的行业大咖来分享关于 IPFS 发控的技术开发干货以及 Web3 的最新动向。Firstly, please allow me to introduce the Web3 Infinity Hackathon to you guys. As a crucial sub-event to fill Singapore Summit, we've already received hundreds of applicants for this hackathon. The number is still growing up, so please don't hesitate to submit your project for dev post before 11:45 August 17th, Beijing time. The registration portal has already been opened on July 1st. All of these qualified projects are welcome to join us. At the same time, Forest Community will surely continue to invite industry experts to our live stream to share useful knowledge about developing with IPFS Filecoin and bring latest Web3 insights for everyone. OK，那我们话不多说，接下来我们就回归主题我来为大家隆重的介绍一下今天的 workshop 嘉宾，来自 Fluence Labs 的研究员 Bernhard Borges，为我们介绍 Fluence and Aqua。那 Fluence 是为开发者提供协议、基础设施和工具，那以此来支持去中心化网络上的应用程序和后端进行去中心化计算。本次课程呢 ，Bernhard 也将会详细的去介绍如何使用 Fluence 协议以及其专门构建的分布式系统编程语言 Aqua 来快速有效的创建和实施 Web3 协议和相关的治理模型。So now let's get straight to the point tonight. Let me introduce you Mr. Bernhard Borges as a research scientist from Fluence Labs. We are delighted to have him tonight to talk about Fluence and Aqua. Fluence provides the protocol, infrastructure, and tools to enable decentralized computation for applications and backends on peer-to-peer networks. In this course, Bernhard will demonstrate in detail how to build and deploy Web3 protocols and associated governance models using the Fluence protocol in Aqua. It's distributed system programming language in a quick and efficient manner. 那接下来我们就让 Bernhard 开始今天的课程。Now, let's give the floor to Bernhard and start off today's workshop.
Hello, welcome to the Web3 Infinity Hackathon. I'm Bernhard with Fluence Labs, and today's workshop from the Fluence team is how to build decentralized peer-to-peer protocols and applications with Fluence and Aqua. What is Fluence? Fluence is a decentralized peer-to-peer compute protocol, network, and tooling, and the network is actually not Fluence's network. Fluence is bootstrapping a peer-to-peer network that allows nodes that are to compute with the protocol to interact with each other and provide generalized compute capabilities. All the protocol, the network refers to network pieces, and the tooling are all open source, Apache 2, very permissive license. You've probably seen this, the progression of Web 1 or Web 2 to Web 3 many times. So I'm not going to go into it in too much detail, but the point here is that there is evolution. Evolution is usually driven by constraints, which could be business constraints, regulatory constraints, and just market demands. And Web3 is really hitting on a whole bunch of requirements and desires these days, both from a business side and from a management of business continuity, and from individuals being able to move freely across platforms and not have their data taken from them. So the really important part in the Web3, enabling the Web3 ethos, is actually peer-to-peer. Peer-to-peer decentralization opens up a vast menu of value that we group as Web3, and this includes censorship resistance, reduced deplatforming risk, control over your own data, democratization of access to applications and software in general, and of course, democratization of value capture distribution. Instead of building entire SaaS companies on top of the back of OSS applications without software, without sharing anything, maybe there are other models available that are more beneficial to the large community building these open source software components. And a lot of this is truly only enabled when you bring together peer-to-peer and decentralization. I mean, decentralization is a bunch of servers is easy. That doesn't unlock Web3 attributes. Peer-to-peer decentralization does. And if we look at so the dominance of certain players in the market, you see where the negatives actually are exactly what the Web3 community wants to rectify. So censorship resistance, we don't want to have high exit barriers. So you don't want to be stuck in a walled garden with your data basically holding your data holding you hostage because you can't leave. We want to enable OSS rewards, not exploitations. Want to reduce deplatforming risks, and on it goes. And this is truly able with peer-to-peer decentralization. So it's not surprising that in the Web3 community, we want to decentralize everything. And I think we've seen the job in the financial system, crypto, smart contracts, DeFi, even though lately the news hasn't been that great, and there might be a regulatory step to be taken. Fundamentally, the genie is out of the bottle, right? I mean, what the current decentralized ledger or distributed ledger technology has brought to the table is how to deal with digital currencies, e-money, if you will, while managing double spend very effectively at a low cost and very, very high probability. And e-money's been around for a long, long time, and this just hasn't been solved before. So if you look at the efforts from central banks in the digital currency efforts, that genie is not going to go back in the bottle. You're going to start building on the same type of infrastructure. Give or take some changes, maybe even existing infrastructures, existing fat blockchain protocols could be hosts depending on the country. And once you have this transactional distributed ledger with this immutability, obviously it makes sense to continue to process transactions data, if you will, right at the source, which means EPMs are equivalent and smart contracts. So this entire subset of the financial system is only going to be growing. How exactly, if the current players are going to be dominant, that's a different story. But the technology and a lot of the Web3 attributes we're looking for is still going to be in play. However, we want to not just deal with financial systems with this vertical. We actually want to decentralize a lot more layers of the internet. If you look at storage, for example, Protocol Labs with IPFS Filecoin's done a great job introducing content addressability, really opening up how you manage data, how you look at data, how you address data, how you access data, and how you package data into much more complex models with IPLD, for example. And that's really, really important because it gives you an interoperability at the data discovery and consumption level that just hasn't been there before. You add to that peer-to-peer hosting, and you get extremely or potentially extremely robust, relatively low cost and comparatively low cost systems with tremendous availability and failover. Another aspect is identity. I mean, digital identity has been bandied around as long as e-money, and over the last 4 or 5 years, between decentralized identity standards and verifiable credentials, you start to see some coalescing of solutions coming about, whether it's using Ethereum wallets for login-based systems or much broader linked data type structures to build actually fairly complex identifiers across data sources way beyond just logging in. However, just logging in is interesting because obviously if you use this current cryptographic driven model, you're not giving your passwords hopefully you should never, but ends up all the time that people are too lazy to hash them to leak them to the broader community, black hat or otherwise. And then on the networking, we want to decentralize a lot there. I mean, take social networks, for example. People are being held hostage, literally, as I mentioned before, by their own data. And that's just, I mean, that's just atrocious. Not only are they being held hostage by their own data, actually there is a monetization level going on that's sickening. And we might see some regulatory pressure to force these data silos, the Facebooks of the world, to give people back their data. And once you have it back and you actually write the appropriate transformation steps, you actually start using IPFS, the file control this kind of data, you then really start being able to control your own data, move it around, make it available to applications you want, like Mastodon, for example. And that's super, super exciting. And again, this is truly accomplishable with peer-to-peer decentralization. And lastly, of course, we want to decentralize computing. And this is where Fluence comes in. So there's a long way of getting there, but this is where Fluence wants to play and is playing. And so if you look at decentralized computing today, you have smart contracts with on-chain computing. So the smart contracts are deterministic and have certain limitations. And obviously, blockchains are introverts. So you have to work with off-chain, and so smart contracts play a big role, but it's actually a small role, important but small. And then you have decentralized places, Golem, LivePeer, for example, vertical, very strong at LivePeer, for example, in video transcoding, a lot of codecs going on, very complicated, heavy lifting, strong hardware underneath it, but it's a vertical, it's not generalized. Also have on-chain management, the entire ecosystem, so very, very cool, but vertical. Where Fluence comes in is basically general purpose peer-to-peer computing. So fundamentally, any business logic you're able to express, you should be able to implement and execute. And as part of that computational model in a peer-to-peer decentralized manner, we're looking at function addressability as being sort of roughly the equivalent of content addressability. We're looking at bringing a universal runtime for WebAssembly IT to the market, which is available today. And we're looking at bootstrapping open permission networks. So Fluence, decentralized peer-to-peer compute. What is it? Where does it leave us? How does it work? So if you look at the diagram on the right, you got the two green circles, which could be lib P2P, well, peer-to-peer clients. Everything on Fluence is built on lib P2P. So that's the underlying peer-to-peer substrate. And so you can have these green ones are clients that are part of the network, but maybe not fully connected. So it could be a browser. It doesn't have to be a browser, but everything in Fluence runs on the browser, as well as other type of clients and nodes. And so we have those two green ones, basically an exit and an entry point, which could be or should be different. And we get the network, which is the blue rounded squares. One's labeled relay. Relay is just a publicly accessible peer. All three of them could be relays, maybe they're not. There could be nodes behind NAT, for example, or peers behind NAT that are not directly accessible from the public, but through a relay. And of course, if our clients are browsers do not maintain long connectivity, so we need a relay to get back to the browser. On these nodes, we can host services. So services are comprised of WebAssembly modules, and the combination of unique service IDs associated with the services, as well as the peer ID, gives us a function addressable tuple, which is used heavily throughout the Fluence system. These services could be in business logic, and that includes quote-unquote adapters. So you can write WASM services, WASM-based services that connect with your existing APIs, microservices, and of course, other peer-to-peer protocols and networks like IPFS. So a peer-to-peer network, we have peers that host WebAssembly type-based services, and these services fundamentally can encapsulate any kind of business logic, including adaptive logic that allows you to integrate with legacy Web 2 and also alternative peer-to-peer networks in a seamless manner. Now, how do you actually get to these services? These services are not JSON-RPC or REST addressable. They're, as I said, they're function addressable, and that's actually happening over the peer-to-peer layer. So there is no JSON-RPC server, REST server that allows you to access each one of these services. Instead, we use Aqua, which is the Fluence peer-to-peer programming language, particularly and especially developed for those use cases. Now, let's just run through the real quick example. If we assume those green clients are our browser, two different browsers, and we want to send a message from the upper left browser to the lower left browser, and the message is, I don't know, :+1 Web3 rocks. And our services are an emoji injector and a spell checker. The emoji injector basically scans that text and says, hey, if there's a series of characters that represent an emoji, we create a URL to the PNG and corresponding PNG. And then a spell checker, obviously, quite just a spell checker. So what we're saying now is, so we have this text, and we now need a script. We now need, which we write in Aqua, that basically outlines workflow. So the workflow is basically take this text, find the emoji injector, update the state of the text to reflect the emoji inclusion, which of course :+1 is thumbs up, and then find the spell check service and spell check and clean up the document. And then we could say, hey, we want to deliver to the lower left client browser. And at the same time, we want to write this text, this clean text, now this marked up text, to IPFS. So this is our workflow. This is what we have. And this is sort of then how we run through it. And this is what we do with Aqua. Aqua is here to basically compose existing services into a logical workflow. And you write the services for the most part in Rust, WebAssembly, and Aqua, as I said, is its own language. So what does Aqua look like? Let's just get right to it. So basically what it does, it allows you to program at a very high level some very, very relatively complicated interactions with the peer-to-peer network. In this particular case, we have a check utility function, and we create a data structure struct in Rust, for example, that basically takes the PID and the service ID. So this is our function address. And somewhere out in service, we have somewhere out in the network, we have a service, which is basically an IPFS command line service that basically takes parameters from a content identifier, which we do by giving it a multi-address. And we'll look at this function in detail later, and the content identifier. And we return a bunch of function addresses. The actual Aqua function here is basically check utility addresses. So that takes the CID from here, the multi-address from here, and it also takes the node to which IPFS is a sidecar. So basically every Fluence node, reference node, which is written in Rust, has by default a IPFS sidecar. So that node, which is actually the peer ID of this particular node where we have the sidecar, and then we deploy a service which has a unique service ID for this particular IPFS service, and we return a bunch of function addresses. So basically what we're saying now is, so we're saying, we are on some node, on this relay node, for example, and what we're saying now is from that node, it's like, hey, do a topological switch to this node, this peer, where we have our IPFS sidecar want to interact with, and create a binding to this interface in Aqua to the deployed service. And we do this by obviously this namespace relative to this service that we've given here. And then we actually run this namespace, the function of this namespace, with the IPFS multi-address and content identifier, and we get back some, which just happens to be an array of function addresses. And then we return those function addresses from this node back to wherever we're at And in this particular case, back to the initiating peer, which actually was, if we go with the little green ones, would be, your browser or your node application or your whatever client peer you were using. And this is all. So you don't have to deal, when you write this, you don't have to deal with a peer routing, because if you go from relay to this node, if you go from relay to one of those nodes, it doesn't have to be a direct connection, right? You actually might up going through a bunch of other nodes, which, by the way, everything is end-to-end encrypted, so it's not a big deal going through a bunch of other nodes other than latency and having optimal routing algorithms in place. Which, again, if you look at this, you don't have to deal with. Same on the way back, you don't have to find your relay node. All this is taken care of. It's not magic; it's just taken care of for you. So we've talked about WebAssembly and we've talked about Aqua. So Aqua basically is a language, a compiler, and a virtual machine. And Marine is a general purpose WebAssembly runtime that is available on every Rust node and executes those WebAssembly modules that comprise those services we just discussed. Aqua VM is also available on every node and every peer, including browsers. And it basically allows you to process this workflow at the peer level. And if you go back to the original, if you go back to this diagram, you saw that we're not calling REST or JSON-RPC, right? We're pushing this through. The workflow is just discover the next service, keep going until you reach the end of the workflow. So this not only makes for very thin clients, it's a data push model, which is very different from your traditional client servers model. And in order to get this really working, is you need smart packages or a smart package, and we call this a particle. So part of the data structure that combines data, the execution sequence, which is the compiled Aqua, and some metadata. And you package this up so that we have our text, right? We have our script to go from here to there, emoji checker, spell checker, blah, 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 right to IPFS, delivered to the other client. This is mapped out in Aqua. So on this node, do this, on this node, do that, where we don't really need to know how to discover that node, how to route to that node, just specified, and compile this into the intermediate representation, which then gets processed by the VM. And the VM basically just checks, hey, what's been executed of this script, of this workflow. It marks it up. There's some signatures signing going on, and it keeps updating the state. So you find the peer with the service you want to find. You in Aqua VM, so now we drive the execution of those services on Marine, apply the state changes, update the script, including the list of peers, create the new data, update the particle and the smart package, and keep progressing through the workflow until we hit the end. And that's obvious. This is an amazingly interesting way of dealing with peer-to-peer computing. It actually allows the implementation of generalized peer-to-peer compute, not just particular applications, but general applications, general business logic expression. So we're halfway through, so get rocking here. Tooling in a nutshell. Let's just be really, really quick. It's not entirely complete, but it's close. So we get a Rust SDK, which allows you basically assembly services in Rust, which then cross-compile to WASM-IT, WASI modules. And it has some additional benefits. Not only does it have a REPL, so you can try out modules locally, but it also has an interesting testing capability that doesn't just test the code you write, but actually tests in the same unit and the integration testing environment as your code, the actual modules you compile to, which is super, super helpful to be able to do that locally and to establish linkage among modules into quote-unquote services as if they were deployed and test them locally. So this is extremely powerful. We have a Fluence JS tool, which basically allows you to create peer-to-peer clients and peer-to-peer nodes. They're not quite as full-fledged as Rust, so through long-running node apps, obviously, than the Rust nodes, but they have a lot of capabilities, and they're very, very useful for, particularly for certain aspects where you are not averse to actually running your own node. Fluence JS brings Aqua VM to a variety of clients, browsers, node apps, etc., and it brings a limited marine virtual machine as well. The limitation being that to the browser and node apps, the limitation being that it only runs single service modules, WAS modules right now. But if you have that, you can deploy these kind of services just like you would on a Rust node and fully access them through Aqua VM. As part of the Fluence JS, it allows you easily actually to expose TypeScript or JavaScript interfaces to be consumed and integrated into Aqua workflows as well. Keep in mind, you are running the client and or the long-running node app. Then Aqua, it's a high-level language, the compiler that compiles the high-level language into an immediate representation, which is then processed by the Aqua VM, and it brings a CLI to the table. We are working on a new CLI called Fluence CLI, but Aqua CLI right now is quite capable. And then we have a bunch of libraries, Aqua Lib, which is a standard library, a lot of convenience functionality brings to Aqua. We got an IPFS integration. We have a services and discovery and publication called Aqua Registry. And there's a bunch of more there's a bunch more to come, and some very, very soon. And obviously we'll keep building and asking community to contribute to building more libraries to make this ecosystem super, super productive. All right, it's time to get to the code demo and review. And the problem we're trying to solve in the code, we'll get there in a minute, is basically we want decentralized blockchain gateways like Infura. We all know, most of us know how expensive it is and how resource consuming it is to run L1 nodes, particularly if it's an archive node. And so it's no surprise that gateway providers like Infura, Alchemy, and many others are doing extremely well, because it's obviously much cheaper, much more effective, particularly for exploration, early development, starting up, to use these gateways rather than run your own infrastructure. Unfortunately, that introduces a very significant centralized component, which really undermines the D in your dApp. So one way to solve this problem is through the centralization problem, is through verification by replication using Fluent off-chain compute. And basically, so in this particular example, we use 3 gateways: verification by replication, you get it, right? And in this particular case, we want to get from each one of those gateways the most recent block number of the L1 Ethereum main chain. That's what we want to do. And we want to have some availability guarantees. So we call each one of those services on each one of 3 nodes. So for a total of 9 responses, right? So we do 9 requests, 9 responses. Also, we'll discuss this a little bit later, hopefully. You don't necessarily can assume that all nodes are trustworthy. They might be nefarious. So building it out this way, there's actually a way to start checking whether each one of the nodes actually gives you back the values you're expecting. Because if you call a gateway I on each one of those nodes, you expect, even if I is divergent from J and K, you would expect that it would be consistent across the nodes. If not, you got a problem with one or more of the nodes. I'm not going to get into this anymore in this example, but it's something to keep in mind. Once we have the request in each one of those responses, our workflow is to basically join all those responses and then calculate a quorum. Basically, the quorum is a calculation of the highest number of occurrences of identical values, basically a mode. And then we provide a quorum threshold to our application, for example, 2/3, that if the mode relative to the frequency is greater than the threshold, then we have a quorum. So for example, we have n is 9, right? We have 9 requests, so we expect 9 responses. We want to have at least 6 of those values equal. So 6 of the block numbers or block heights should be the same in order to get a valid quorum, which leads us then to a valid or invalid point estimate, the actual block number. So what are our implementation requirements for this? It looks, I mean, it looks a lot more complicated than that. You get it, but there's parallelization in there. And we'll have to talk about this in a minute too. So we need to implement our WebAssembly services. And at the very least, we need a way to query gateway providers, right? And we need to do all these quorum calculations, which we just discussed. We also need some Aqua code that composes the gateway provider calls and the quorum calculations into a workflow. And in this workflow, we also want to add the appropriate control structures. So appropriate control structures. As you may know, WebAssembly has certain limitations. One is it's single-threaded, they're single-threaded, and two is no sockets. We need sockets in order to call those gateway providers, and we need FaaS control structure. We need parallelization. Otherwise, we might end up at, it might be too slow. So we actually may legitimately end up at different block numbers because we might just hit the end of the block time because we're so slow that we hit one before and one after. And that would be a legitimate case, which would be very difficult for us to ascertain. So we want to be as quick as possible. And we do this with parallelization. As I just said, WebAssembly is single-threaded. So where does parallelization come from? It comes through Aqua. Aqua allows you to parallelize the call of services through whole different topologies, different nodes, different peers. And then you basically join these results and you get a very, very quick execution in parallel. Parallelization is based on unique service, which could be on one node. So if you want, say, 3 arms for your parallelization, you deploy 3 services on one node, or it could be on 3 different nodes and you just call across its different topologies. Okay. So what are our implementation steps? We implement those WebAssembly modules in Rust. We configure and deploy our services. So we build Rust modules, then we configure those modules into quote-unquote what will be services. And then we deploy them to one of our nodes. And then we implement our Aqua service and composition and control script. It doesn't necessarily have to be in this order, but those are sort of the 3 major steps. And then we, of course, run the service. So let me switch real quick here. And let's get to the code. So I hope that's big enough. So before we dig in too much, in order to call these gateway providers, we use JSON-RPC as our common denominator. Most of the service providers have advanced APIs available, but they're all different. So the easy way is to actually use JSON-RPC, which is the base access. All these APIs, all the Web3 libraries are built on because this is how EVM RPCs service respond. And so this is a typical JSON-RPC setup. You got the version, you got the method, which is underscore block number to get the most latest block number. We don't have additional parameters, and we have an ID, which is literally a nonce. And then if you call this with curl, for example, you end up with a result. If there are no errors, it gives you back the version, it gives you back a nonce, and it gives you back the result, which is actually a hex encoded latest block. So let's just have a look over here real quick. So what do we need in order to get our service done? Our point estimate across multiple gateways into a single block number. And don't be fooled by the block number. You can extend this to any other scenario and actually get valid block numbers. Is quite interesting when you ping each one of them because they all use Web2 technology, so there's a lot of caching involved. And that may not necessarily refresh at the rate blocks actually are generated, which is, I mean, it would be tragic given that you have 13 seconds, but it does happen. And so if you look to the left here, we basically have a directory for our Aqua scripts. We'll look at them in a minute. We have artifacts. Artifacts is basically, it collects all the WebAssembly modules we are creating. And we just move them from each one of the individual Rust projects into the artifacts directory, so it's easily accessible, so we don't have to have these long paths into each one of the compile directories for each one of the services. We have a config directory. That's where you have a few configs in there. A little cleanup, sorry. And some old stuff, don't worry about that. Parameters, we'll go into this in a minute. And scripts, this is our build script on how to basically compile Rust into WebAssembly modules. And this is actually our business logic. This is where our WebAssembly modules are created. So we have multiple ones like curl adapter and multi-provider query. So let's just have a look at this query, because this is really where we want to call each one of those providers in a consistent manner, and we have it set up. So here, this is important. This is the marine macro. Can think of it as a decorator, which basically does a whole bunch of things, including type checking, because we only pass by value, so only the most basic types in Rust are available. There are no generics, there are no trade objects, there's nothing complicated. It's just basic types. And we then return a custom struct, which we call EVM results. And this is declared right here. So basically it returns the provider. So Infura, for example, the name, standard out and standard error from the curl call, which we have to use. Why do you have the curl call? We'll get this in a minute, maybe faster. So I told you before that the WebAssembly IT doesn't have any sockets, and we need to make these calls. The way we make these calls is we actually have a way to punch through the WASI sandbox into the host system through permissioning, and then use, as permissioned by the host, particular binaries, including curl. So basically what we're doing is we're using curl from this WebAssembly module and make our call to the provider, where the provider info included the URL and the name. So this would be Infura URL, and this would be, the name would be Infura Alchemy. This would be Alchemy link, would be link. And so here is where we get a curl response. So how does that happen? Basically, we're linking in a curl adapter. And that curl adapter we have to write, and it's actually right here. And basically what this does is, again, we are marking as upper marine. Basically what we're doing here is we're FFI linking the host, which is literally the peer you're running that service on, and FFI link the curl binary command. And this comes through mounted binary result, is basically the way we capture output from a binary and bring it from the host into the WebAssembly module. And we basically wrap that curl command, and it doesn't have to be this way, but we're doing it this way. We call it curl request. And it takes basically an array of strings, just like you always would, subprocess, etc., and to run your curl command. So back to the multi-provider. Now here we actually are quote unquote linking to, we're not importing, we're linking, it's an FFI import, we're linking to this curl adapter through this command, and we're now bringing in that curl request wrapper we just saw. And we're using this in this module, where once we do here get the curl response, this is what we're doing. We build all these parameters, and we build these structures for JSON-RPC, and we run it, and we get the response. And if it's all good, we basically convert the hex into radix 16 through radix into an int. Right there, we split off the hex identifier 0x, and then obviously our radix is 16, and we ending up with the U64, our block height or block number, and then we just return this as a standard out. And what we're actually doing is we're creating a JSON string with where the key is block height, and our value is the U64. So this is what we got. And what we're doing now is we basically say, hey, let's compile all this. And while we're compiling all this, we actually look at the script, the build script. So this is the build script I'm just running here. Hang on, let me just maybe bring this back up together so we see a little bit more. Well, this is okay, it's compiled already, so this is fine. So basically what we did is we ran this script, and basically what we're doing here is we're creating this artifacts directory where we then deposit all our WebAssembly modules for subsequent use, including uploading. And so we CD into this lots of modules. We run each one, we compile each one of the services or modules. And the key there is to basically everything else. The key is here we do marine build release. This is what gets you the WebAssembly module. And then we just copy that from the local target directory into the artifact. So those are the outputs here. Okay, so once we have those, we can actually play with them in our local REPL. Let's see if I have something here. Yes. So I showed you the configs file, and this is where we specify how we load modules. And let's just have a look at this real quick. It's right here. So this is how we specify our dependencies and our module specifics and how much memory we want to allocate, and if necessary, what the mounted binaries are. And if you look at it, this is basically, these are all the from each of the modules, the exposed through marine interfaces and functions. And so if we want to call to the multi-provider query get block number, which we just looked at, we basically use the link one. It doesn't use an API, so I'm not giving anything away. And if we run it, we basically, oh, look, we get the most recent block height, and it is exactly this JSON string we're expecting. So far, so good. So we have a whole bunch of modules. We obviously don't have enough time to go through all of them, but I think you get the gist. And so let's have a look at the Aqua. So here is, there's multiple functions. Go through README because I'm building it up in the READMEs, but this is sort of the last part. And the last part is interesting for a variety of reasons. So basically what we're doing is we're giving a bunch of function addresses into the, use them in the function signature, which includes CID. So basically we took some parameters and instead of feeding them directly into the function, into the Aqua function, we actually uploaded those parameters onto IPFS, and now we're feeding in the IPFS CID and multi-address, and run this through this Aqua function. So one of the things we have to do first is basically convert the IPFS documents into the various parameter structures we want. And once we have this, we basically remember the diagram where we had all these services and then the nodes. So basically for each address, we basically on each node, we want in parallel, we want to write for each provider, we want to run this get block number. So this is each provider, basically the URL, provider name and the URL. And we'll run this. And then we join it, then we get a calculate our quorum, and then we actually do some deviant identification, deviant being service calls that do not correspond to the quorum. And then we print this out as an intermediary. There's a lot to be done with that. Have a look at the README, and then we return basically the quorum and whether or not it's a valid quorum. And if we actually run this, it looks something like this. And video is sucking up a little bit more bandwidth than I would like. All right, so we ran the nine calls. We have no deviants in there. So basically you see this is the most recent block number we were looking at, and this is the frequency. So all gateway providers responded with the same value, which is super, super cool and makes us very, very happy. But if it didn't, then, you know, here the quorum number was 2/3. We can make decisions based on that. Okay, so that was a very, very quick run through some of the code. And have a look at README. All this is in the repo I mentioned earlier, and it's at github.com/Fluence Labs /examples/Aqua-examples/decentralized decentralized blockchain gateway. You just need to know it's in the examples directory and you'll find it. So going back to a couple more things, we got 3 minutes. We have multiple available integrations, Fluence IPS, for example, Ceramic, Near. We got additional building blocks, adapters, integrations, NFTs, verifiable credentials, DIDs contributed from the community. And now to the big part. Fluence has, for the best use of Fluence on Aqua, there are 2 prizes available at 2,500 USDC each. And just a few ideas to look at. So any kind of complex computation you can use for your DeFi NFT project to off-chain Fluence network, anything that takes centralized joke points out of your dApp are great. Build data processing engines for IPFS Filecoin. Build an IPLD indexer, reindexer. So as I briefly showed, you can use CIDs and then IPFS documents as inputs into your Aqua function. I mean, any function. In this particular case, of course, it's the Aqua function. And that has a lot of advantages, aside from the fact that you basically have an immutable content addressable and discoverable reference to your parameters if you want to share it, if you rerun it, if you don't want to mess up your own parameter. This is one way of doing it. However, the bigger benefit is you can actually represent fairly complex data structures, linked data structures, very succinctly, and that through IPLD actually. And this is actually extremely powerful. And then re-indexing IPLDs, if your parameters change, for example, if you have these linked parameter structures, that also would be a really cool project, I believe. Another really cool project would be to basically use DAO proposals to trigger off-chain compute. So if you create a DAO proposal, you can literally attach IPFS-saved compiled Aqua scripts to the proposal that if your proposal gets accepted, you actually can immediately launch the execution of some off-chain compute associated with the proposal, whatever it is. But this now brings you a very interesting, cryptographically interesting, immutable code capability on the off-chain side to things like DAOs and further your automation capabilities literally through voting. And this is something we're very excited about, and we would really like to see people to maybe spend some time on it. Anyway, thank you very much for listening. Thank you for being here. Thank you for having me. You can reach us on GitHub, Discord, Telegram, Twitter, all the good stuff. And of course, we are hiring. If you're interested in any of the projects, if you're interested in Rust, compiler creation, etc., language work, please stop by, have a look, and apply. Okay, and this is it. So thank you very much, everybody. Have a great hackathon. We're super excited to be here, and I'm very much looking forward to your contributions. Cheers.
好的，我们这边也非常感谢 Bernhard 给我们带来非常精彩的课程。那相信大家听完以后呢，对于如何使用 Fluence 协议和其专门构建的分布式系统编程语言 Aqua 有了一定的了解。那如果想要继续去深挖一下他们的项目，也可以按照 Bernhard 刚刚提到的一些方式，去他们的官网、去 GitHub 去参考他们的代码。那对于想要重新学习一遍，或者说错过了本次直播的朋友们呢，那也不用担心，我们所有的中英双语的直播教程都会上传到原力区的 B 站和 Force Web3 Community 的 YouTube 频道，那来供大家之后的参考和学习。All right, thanks so much for Bernhard to giving us this amazing sharing. I believe all of our audience must have a deeper understanding toward how to use Fluence and Aqua. So for those who want to watch it again or fail to attend in time, don't worry. All of our live stream videos will be uploaded to our Bilibili and YouTube channel respectively in Chinese and English. Make sure you check them out. 那到这边呢，今天的直播分享也差不多结束了。我在这边呢，也再次鼓励大家来报名参加我们的 Web3 Infinity Hackathon，来分享丰厚的$100,000的奖励。同时呢，也希望朋友们可以持续关注我们园区区。我们的下一次直播呢是在本周五晚的6点，也是同一时间，不见不散。That's all for today. I'd like to once again encourage you to sign up for Web3 Infinity Hackathon and share the huge prize of over $100,000. Meanwhile, don't forget to tune in our live stream channel, and our next live broadcast will be at the same time this Friday. See you guys at 6 p.m. this Friday.